Today with Unit 9, Part A, which is on optics. Part B will be all about the properties of light and the characteristics of light. Part A, when we say optics, what we really mean is mirrors and lenses. So today, we're going to start with our topic of the day, which is mirrors and mirror ray diagrams. Oh, that was a bad line. Take 2. Mirrors and mirror ray diagrams. Now, before we begin here, you are going to need all of the following materials. You're going to need a ruler. You are going to need a compass. You are going to need a protractor. And lastly, you are going to need a metal spoon. Pause this video, go collect all of these items, and when you have all of them, come back and resume playing. If you're back here with us, I'm going to assume that you do, in fact, have all of these items. That you have a ruler, that you have a compass, that you have a protractor, and that you have a metal spoon. Oh, that is not what we want. Try that. Okay. So, here's what I want you to do, is I want you to start with your metal spoon, and I want you to do this. I want you to take your metal spoon, and I want you to hold your metal spoon a good distance away from your face, and look and see what you see. Then I want you to take your metal spoon and I want you to bring it all the way up to your eye, so close to your eye that it's actually almost touching your face here. And I want you to close one of your eyes and try to see if you can find the reflection of your eye in your metal spoon. Then I want you to take this metal spoon, I want you to flip it around so that the scoopy part is facing away from you, and I want you to look at your reflection once again. Here's what you should see. You should see that when you have the scoopy part facing you, you see yourself upside down. When you bring it really, really close, you see your eye looking ginormous, and actually, if you pay attention, it should be right side up. Then if you take the scoopy part, face it away from you, you pull that spoon away from you, you should see yourself right side up, but it's like a mini version of yourself. It's like you have the 0.5 filter on your phone. All of that in one spoon. Today we're going to talk about how that works. How does a single spoon make all of those different images? We're talking about mirrors and mirror ray diagrams. Now, here's what we're going to do is we're going to start by drawing a mirror. And I'm going to teach you in this lesson all about how to draw mirror ray diagrams, which are what's a light ray diagram when you have light rays that are interacting with a mirror. And as we draw those diagrams, it's going to reveal to us a lot about how mirrors actually work. So what we're going to do is we're going to start by drawing a very, very simple mirror. This is what we're going to call a plane mirror. Anytime we draw a very simple mirror like this, or any kind of mirror really, we start by drawing a principal axis. So here's what I want you to do. Take your ruler, lay it nice and flat on your piece of paper, and draw a nice flat line through the center of your paper. Then, after you draw a nice flat line through the center of your paper, you're going to draw another line that intersects that line. Something like, something like this here. We're going to see how this goes because I'm trying this on like this little thing today. I am not doing this on a piece of paper. So really, I have no idea how this is going to go for us, but we're going to try. Okay. Oh no, already I'd say it's going mediocrely. Okay. Here's what we're going to do, is we're going to start here by drawing a plane. This is what we call a plane mirror here, and we're going to see how a plane mirror works. Now we call this a plane mirror not because it's boring and uninteresting, but because it only operates in one plane. What we see here is this is the kind of plane that you would have, or this is the kind of mirror that you would have in your bathroom if you're brushing your teeth in the morning. You would have you standing on this side of the mirror here like this with your little toothbrush. And then you'd have the mirror in front of you, and on the back side of the mirror, you'd see like a fake version of you. Like here would be you on the back side of the mirror with your little toothbrush staring back at yourself. We call this side of the mirror where you actually are, this is what we call the real world, because you really are here. We call this side of the mirror, back where you see yourself as being, but you're not actually there, we call this the virtual world. This right here, this line that's dividing, this is like a side view of your bathroom mirror. Now here's what we're going to do is we're going to draw a little diagram to show how mirrors actually work. And when we draw this diagram, we're going to draw an object on the front side of the mirror. Now anytime we draw an object on the front side of a mirror, the way that we always draw an object is we always draw an object like this. Whoop, whoop, whoop. We always draw an object as an arrow. And you say, Ms. Wilson, that's very interesting. Why would we draw an object as an arrow? Well, because that helps us tell if a image that we're going to see in the mirror is going to be reflected right side up or upside down. You saw that if you take your little spoon and you hold it out in front of you, a lot of times you're going to get some sort of image that's you but flipped upside down. So when we draw the object as an arrow, we can see clearly this is the top of the arrow, this is the top of the object, this is the bottom of the object. If this were your toothbrush that you were holding up in the mirror, this right here could be like the bristles of your toothbrush up at the top. Down at the bottom, you could have the base of your toothbrush down here. So this is the top of the object, this is the bottom of the object. Now here's what we're going to do, is we're going to draw a little line here that goes, oh wow, this is going to be nearly impossible. Okay, we're going to draw a little line here, and please be patient with me as I try to figure out how to do this. We're going to draw some light rays that are coming off the top of this object. Now here's the truth, is that in reality, at any given point in time, light rays are coming down from the ceiling or coming down from the sun or coming down from any light source, and they're hitting all the objects all around us. And when those light rays hit the objects, well, those light rays bounce off of the objects in every single direction. So right now, if this was a little toothbrush in your bathroom, situation, if this were a little toothbrush in your bathroom, you would see that right here, please excuse the bells. You would see that right here at the top of this toothbrush, you would have light coming down from the ceiling. That light would hit the top of the toothbrush. When that light hits the top of the toothbrush, it's going to scatter off the toothbrush in all directions. Some light rays are going to go this way, some light rays are going to go this way, some light rays are going to go this way, some light rays are going to go this way. Well, what we're going to do is we're going to start by drawing just one of the light rays that would come off the top of your toothbrush. Well, one of those light rays would hit the top of your toothbrush, and when it bounces off the toothbrush, it would head straight for the mirror. So let me see if I can draw this here with my ruler. Let's draw a light ray that starts at the top of your toothbrush and heads straight for the mirror like this. We always draw arrows on our light rays showing which direction they're headed. Now, this light ray would hit the mirror going this way. Well, there would be some other light rays here too. Like, there might be a light ray that starts here, okay, here at the top of your toothbrush and bounces off and goes this way. There might also be another light ray that starts here at the top of your toothbrush, like this, and goes down this way, like this. And so you'd have all these light rays bouncing off of your toothbrush, off the top of your toothbrush. Now, when each of these light rays hits this mirror, it is going to reflect back. And when it reflects back, it is always going to reflect back according to this law. And the law that it's going to follow is always going to be the law of reflection. The law of reflection says, as we've discussed before, that the angle of incidence is going to equal the angle of reflection, where these two angles are measured from the normal line, which is the line that's perpendicular to the surface that the light ray is bouncing off of. So here, you have this ray coming in. It's going to bounce off at some angle that is the same as the angle that it came in at, oh gosh, no thank you. It's always so hard with the ruler. Where we define our line here as a line, where we define our angle as an angle from the normal here. So this is our normal right here. This is our normal right here. And then this up here is our normal right here. Okay. You can see that this first arrow right here is going to come in at the normal, at an angle of 0 degrees with respect to the normal. And so then it's also going to reflect off at an angle, I can do this, Yes, with your ruler at an angle of 0 degrees with respect to the normal. And mine's a little off there, but you used a ruler on a piece of paper so you could make this right along the same line right there. This one came at an angle like this. Now this is where, if I could, I would take out my little protractor here and I would just line it up perfectly on my page. And I would say, okay, let's see, this thing is coming in at an angle of, I don't know, let's call it 10 degrees. So it should also bounce off at an angle of 10 degrees. Because I don't have a good ruler sort of situation here, or I don't have a good protractor sort of situation here, I'm just gonna eyeball it, but you should actually measure this angle here. I'm gonna say it goes with something like that. And then lastly, this angle right here, you could measure this angle, it'll bounce off going at the same angle, something like this. Now, let's talk a little bit about how your eye would see. Your eye would look at this situation, and the way that your eye sees anything in the world is that your eye looks at the world and then it says, okay, stop, don't do that, please go away. Okay, your eye looks at anything in the world and it looks at the light rays coming off of an object. Here's a side view of your eye looking out at the world. Your eye would get some light rays coming from an object, and your eye would say, where do those light rays come from? And what it would do is it would trace all of those light rays back to where it thought that they originally started. For example, if I had this pen here, and I were to look at this pen, there'd be little light rays that are bouncing off in all directions off the top of this pen. But what would happen is some of the light rays are coming in and are going to hit my eye directly. What I would do is I would say, hey, I got a light ray right here. My brain would say, where did that light ray come from? And it would trace it back in a straight line. And it would say, oh, that light ray came from right here. That must be where the top of the pen is. So here's what your eye would do, is your eye would look at all of these reflected rays coming from the mirror. Once again, please just ignore the bells. Your eye would look at all of these reflected light rays coming from the mirror, and it would say, wow, that is so interesting. Where did all those light rays come from? And what your brain would do is your brain would trace those light rays back to where it thinks that those light rays came from. So what you would see here, and again, I'm not going to be able to do this with a ruler very well, so I'm just going to have to freehand it, and it's going to be really not very good. Okay, so here's what you would see, is you would see that coming back from this one right here, you would get, and again, you should do this with a ruler here. Oh gosh, oh my gosh, this is just truly embarrassing, if we're so honest. Okay, here's what you would see. Try again. I'm just going to freehand it. I was trying to use my ruler. You should use a ruler here to make a nice straight line. So hold up your ruler on your piece of paper. Make a nice straight line going back. It would say, I see that light ray. Looks like it's coming back from this way. Then your eye would say, I see this light ray right here, and it looks like it's coming back from this way. Again, you would do this with a ruler. You would line it up all nice. It would be beautiful. Then it would say, I see this light ray right here, and it looks like it's coming back from this way. Again, you would use a ruler. It would look so stunning. Really just beautiful, stellar performance on your part. And so then your brain would say, oh, I get it. All these light rays look like they're coming from here. This right here must be the top of the object. And so your eye would see the top of the object back here behind the mirror. And your eye would say, that's where the object is. So you would see two objects. First, you would have the actual object, which lives here in the real world. It's a real life object. And I left out a C, a real life object. Then over here, you would see what we call the image of the object. And you would see the top of the object here located at the point where all of these reflected light rays converge back behind the mirror. Now, there are three terms that we are going to use to describe any image that we see from a mirror. The first word that we're going to use to describe it is we're going to talk about, is this image here upright or inverted? Upright meaning it's right side up, inverted meaning it's upside down. And you can see that this image here is upright. If my toothbrush over here is facing up, this one is also facing up. You can see the bristles are up towards the top. The next thing that we like to talk about is this image reduced in size? Is it the same size, or is it enlarged in size? And we would see here, and you know this from your real life experience, that the object that you see behind a plane mirror is the same size. Finally, the last adjective that we use to describe images like this is we like to discuss whether these images are virtual images or real images. Now, a real image is made by real light rays. A virtual image is made by virtual light rays, meaning they aren't actual, there's no actual light back behind this mirror. It doesn't really exist. But your brain is tracing back light rays back here, and it says, yeah, I think that there's a light ray back there, and I think that this is a light ray back there. These are virtual light rays. So we say that this image is a virtual image. It's not made of actual light back here. It's made of virtual light rays that your brain traced back. A few conventions here. We always draw real light rays as solid lines. We always include arrows on our real light rays. We always draw virtual light rays as dotted lines here. So really, I should never draw these dotted lines for my normal here, although it was useful for me in finding my angles, because a dotted line means that's a virtual light ray. Another thing that you need to know, another vocab term here, is that we call this line right here, which is just a straight line at the base of the object, we call this line the principal, or sometimes we call it the optical axis. Now, the principal axis or the optical axis isn't crazy important for plane mirrors, but it gets really important when we get to other types of mirrors like convex and concave mirrors, like we'll see right now. Here's what you're saying. You're saying, Miss Wilson, this is all good and fine, but you see the plane mirror is really very plain and uninteresting, and I'd like to understand what happens with spoons. That is why I'm watching this video today, is to really understand why a spoon creates the image that it does. Why do I get little me that's upside down, and then big me that's right side up, and then little me again that's right side up? I don't understand how a spoon does all these things. Well, you've come to the right place. Let's talk about spoons. I need a new drawing. We're going to start by talking about what you see when you look at your reflection in a concave spoon like this. That's when you're looking into the scoopy side of the spoon. When you're looking into the scoopy side of the spoon, we call this a concave mirror. Sometimes we also call it a converging mirror. And we'll talk about why we use each of these terms. The term concave has to do with the shape of the mirror. What you see with this is that it looks like if you were looking into this little scoopy side of the spoon, it kind of looks like a little cave here, so we call it a little concave mirror. Now, here's what we're going to do is we're going to draw a mirror diagram of a concave mirror. So here's what I want you to do is go ahead and start, not that, bye. Okay, go ahead and start by drawing yourself a principal axis. I'll draw mine right here. This time, when we draw our mirrors, we're not going to draw a nice straight line like we did for a plane mirror. Instead, we're going to draw a nice concave mirror. The way that you're going to do this is you're going to use your little compass. Yay, compass! Okay, here's what you're going to do. You are going to get your compass to a reasonable size. Now, some compasses, like mine here, you can see that my compass, oh, I just really need a camera. Camera. It's coming. You're going to see so soon. Come on, you can do it. Okay, yes, perfect. Okay, my compass here, you see that it has little lines here that measure the centimeters on this side. It also has inches here, but why would we ever in our good world use inches? If yours doesn't have a little measurer here, if it doesn't say how much it's spread, this is measuring, what it's measuring here is the radius of how far apart these are. So I'm going to choose a reasonable radius, something like 4 centimeters here. but you choose something that works for you. If you don't have a little dial like this where you can set it that way, then you can take your ruler, and what you can do is you can put one end right here at the 0 mark, put your little center marker at the 0 mark, and then measure out where you want your little pencil to be, and I'm going to measure it out to the 4 centimeter mark like so. So now my circle that I draw is going to have a radius of 4 centimeters. I take this little compass once I have it all set to the setting that I want it to be on, and then I go to my piece of paper. What I'm going to do is I'm going to put this little thing right here. I'm going to put the little point here right on the center, and then I'm going to just draw a nice little curve here with my pencil. I want to draw a concave mirror. So to do this, you actually do need to use a compass. I literally cannot use a compass on this thing. But here's what you would do with your compass, is you'd start by drawing a little dot here where you want to put the center of your compass. Please label it C. C here stands for the center of curvature. Then what you're going to do is you're going to take the little pokey part, the center part of your compass, you're going to put it right there on that C dot, and then you're going to swivel that thing around to make a really nice curve. Now once again, I can't really do this here like at all, so I'm going to kind of try, and then I just feel like it's not going to work. And so, yep, that's not happening. Okay, so anyway, so I'm just going to draw it with my freehand. But you really do need a compass here in order for this thing to work. So there's my free-handed drawing. Now, here's what you're going to do next, is you're going to take your ruler and you're going to measure another point. So here's something that you see with this mirror, some other parts that you need to label. This point right here where the mirror intersects the optical axis, this is what we call the vertex of the mirror at this point here. And now here's what I want you to do, is I want you to take your ruler, hold your ruler up to your piece of paper, and I want you to measure from C, the center of curvature, to the vertex. When you measure that, you should get whatever you set your radius to be. So if you set your radius to be 4 centimeters, you should get 4 centimeters there. Then I want you to measure in the middle here at 2 centimeters, or whatever your middle point is, and label that dot that's in the middle between the center of curvature and the vertex. Please label that dot F. F stands for the focal point of the mirror. And the focal point of the mirror always lives halfway between the center of curvature and the vertex of the mirror. That's our focal point. Now you have your setup drawn, and you're ready to start drawing a mirror ray diagram. Here's what you're going to do. You're going to start by drawing your object at a certain distance away from the mirror here. Now when we started with our spoon very, very far away from our faces. Let's draw an object that's very far away from that concave mirror. So I'm going to draw an object all the way over here at this point here, somewhere past C, so far away, past C. And now, what we're going to do is the same thing as last time, where we're going to draw light rays coming off of this thing, and those light rays are going to hit this mirror and they're going to reflect back. But when we do that, they are going to follow the law of reflection. Now, you could probably imagine that following the law of reflection here is going to be a very, very tricky thing to do. Why? Well, because isn't the direction of the normal changing like literally all the way around the circle? Whew, that's going to be really, really tricky to define, because here the normal is going this way, and here the normal is going this way, and here the normal is going this way, and here the normal is going this way. So all the way around the circle, where the normal is pointing is actually changing. Now, this could be very difficult, but we do have a shortcut. And the shortcut is all you have to do is follow the 3 golden rules of optics. If you follow these 3 golden rules of optics, you will always be able to draw all of the little light rays, and you will always draw them according to the angle of reflection without using your compass, or sorry, without using your protractor at all. Here are the 3 golden rules. Let's start with the first one. The first golden rule is that a light ray that goes through the center of curvature will reflect back on itself. A light ray, oh, this is so hard because it's so laggy, so I always have to write so slow. A light ray through the center of curvature will reflect back on itself. Let me show you what I mean by this. And this is going to be something where I try, okay, see, this is going to be a really, really, okay, that's not terrible. Okay, this is where you, like, for serious, super need a ruler. And I'm going to try it without a ruler, and it's going to be just super mediocre. Okay, so here's what you're going to do. Draw a line that starts at the top of the object that traces through C. See, I totally missed the top, and I totally missed C. You can't do that on your piece of paper. You really, for serious, have to nail this kind of thing. So you want a line that starts at the top of the object. It has to go straight through C, and then it should hit this mirror right here. That light ray is just going to reflect back directly on itself. So it's going to go back straight this way. Once again, you're not going to have a gap here because you're doing this with an actual ruler in real life. And so you're going to have just such a nice smooth line, and you're going to draw it reflecting back through itself. That's the first rule, is that a light ray that starts at the top of the object, goes down through C, will reflect back on itself like this. That's the first rule. Here's the second golden rule. The second golden rule, actually, I'm going to change my color because I can. Let's go green. Here's the second rule. The second rule is that a light ray that passes through the focal point, a light ray through F, through the focal point, will reflect do it. Will reflect, yes, parallel to the optical axis. Okay, here's how this looks. And again, I'm going to freehand this. It's going to be terrible, but I tried with my ruler and it did not work. If you had a light ray that started at the top of the object like this and then went, oh gosh, started at the top of the object like this and then went straight through F. And again, you need to be right on that dot here. You need to be right on the top of the object. Otherwise, it's not going to work. That light ray is then going to reflect back perfectly parallel here. Oh, and pretend I can do all these things. Oh gosh, this is just embarrassing. When I try to draw a straight line. Okay. I'm just doing it with a ruler. I think I can do it with a ruler. I can't do it with a ruler. It's so hard. It's so sad. Oh, gosh. Okay. We'll reflect back parallel to the optical axis, like this. Okay. A ray that goes through the focal point will always reflect back parallel to the optical axis. Now, again, you need these things nice and tight. Otherwise, it's not going to work for you. Do you see how I started my reflection a little bit above where the incident light ray hit the mirror? Whew, that's not going to work. It's got to be nice and tight and nice and smooth. Otherwise, things are going to look really nasty for you when we try to actually make an image here. The last golden rule of optics, rule number 3. Is that a ray that is parallel to the optical axis, parallel to the optical axis will reflect back through F, back through the focal point. So here's what that looks like. If I could draw a light ray that starts here on the top of this object. Oh no, I tried to use a ruler. Okay, just say, next time I try to use a ruler, just say, Miss Wilson, stop trying to use a ruler, it doesn't work. Okay, if I could draw a light ray that goes straight parallel like this to the optical axis, when it reflects, it's gonna reflect back through the focal point like this. So it's gonna reflect back this way, like so. Here's what you're gonna get. If you follow these three rules, you're gonna get 1, 2, 3 reflected rays. When your eye looks at this situation and tries to assess what's going on here, it's going to see 3 light rays. Imagine if your eye was enormous, not this tiny thing. It would see this light ray, and this light ray. And it'd say, okay, where did all these light rays come from? And it would say, well, it looks like this light ray came from right here. It looks like this light ray came from right here. It looks like this light ray came from right here. Oh, I get it, your brain would say. It would say, oh, it looks like the top of the object is right there, because that's where all those little light rays are coming from. And so you would get, if this is your object, this would be your image. And the image that you would see could be described by these adjectives. You would say, that image is not upright. That is an inverted image. Then you'd say, that image is not the same size. It's much smaller. We would say it's reduced in size. Finally, you would say, that image is actually made of real light rays here. Do you see that this light ray actually really did reflect back? And this one actually is a real light ray right here. And all of these are real light rays that are converging at this point. So we would say that what you have here is an image that is inverted, reduced, and real, because it is made of real light rays. This is why we call it a converging mirror, because this mirror is going to converge all of the light rays at this point. It actually is making real light rays all show up in this place. And so because of that, we call it a converging mirror. But converging mirrors don't always make inverted, reduced, and real images. There's another type of image that can be made with a converging mirror. Let's go ahead and look at this other type of image that you can make with a converging mirror right now. New drawing. Try this one. We're going to make another converging mirror. So once again, get out your ruler. Make a nice drawing of a principal axis here in your notes. Oh gosh, that did not work. Nice drawing of a nice principal axis here in your, wow, that is the most crooked principal axis I think I've ever drawn. A nice drawing of a nice principal axis here in your notes. Okay, good, beautiful, love it. Then what you're going to do is, once again, you're going to take out your compass, get it set to the right settings, make a little mark where you're going to put C, that's going to be your center of curvature. Then you're going to draw just a very nice curve around that center of curvature. Again, mine is not drawn with a compass. Yours is drawn with a compass, otherwise it doesn't work. Then you're going to measure the halfway point. Actually, I kind of want my center of curvature bigger for this one. Wow, so sorry everybody. I'm going to go here for C, then I'm going to go here. Okay. Now I want you to measure the halfway point between your center of curvature and your vertex of your mirror. Label that as your focus here. Now we're going to see what happens if you take an object and you put it in really, really close to the mirror. So let's take an object and let's put it like here, between the focal point and the vertex of the mirror. And we're going to see what happens. Once again, we're going to follow the 3 golden rules of optics. The first golden rule of optics, oh no, I don't remember what color I used. I think I used green. Okay, the first, nope, I did not. I used blue, I remember. Right? We're going to go with that. Okay, the first golden rule of optics is that a light ray that goes through C is going to reflect back on itself. Okay, well, here's the top of my object. Here is, oh wow, okay, that's not what I wanted. Pause. Okay, try again, go away. Okay, here's the top of my object. Here, right here is C. So here's the problem is that I want a light ray that's going from the top of the object to the mirror. I don't want a light ray that's going from the top of the object back down to C because I want a light ray that's actually going to hit the mirror. So what I do is I take out my trusty ruler and I'm going to line up my trusty ruler so that my ruler is making a nice line. It's lined up with the top of this object and with C. But then when I draw my line, I'm going to draw my line just from the top of the object to the mirror here, not including the part that goes back through C. Then what I'm going to do next is I'm going to draw the reflected ray. It says that the reflected ray will reflect back through C. So I draw a little light ray that goes from the top of the object, it hits the mirror, and then I draw it so that the reflection goes straight back through C. And I am not using a ruler, but you should use a ruler, otherwise it's going to get so messy and bad. So please use a ruler or it's going to look like blah, 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 like mine, okay? And that's bad. Here's the next rule. The next rule was that a light ray that goes through F will go back parallel to the optical axis. Now, here's the issue is that my light ray is not going to go through F because I want it to go up to the mirror. So the way that I'm going to draw this is I'm going to start my light ray right here on top of, well, right there on top of my object. And then I'm going to draw it so that it would go back through F if it could. So I'm going to draw it basically essentially like this, except I'm not going to draw this part of the light ray right here because that part of the light ray is not actually there. I'm just drawing the light that's coming from the top of the object. So I start it on the top of the object, I go to the mirror, but when I line it up with my ruler, I see that the top of this object would line up with F. That light ray is going to then reflect back. Oh no, I'm on eraser mode. That light ray is then going to reflect back parallel to the object. Oh my. Terrible. Once again, I know it's awful. Parallel to the optical axis like this. Okay? Finally, rule number 3 says that if you have a light ray that goes parallel to the optical axis, that light ray will reflect back through F. So I draw a little line starting on the top of the object that's parallel to the optical axis, and then I'm going to draw it back through F this way. This time it actually can go through F, so I'm going to draw it back through F like this. Again, you should really be nailing everything here. Everything should be nice and tight. Here's what your eye would see. If your eye were looking on, your eye would see 3 light rays here according to the 3 golden rules. Now, of course, you would see more light rays here. These light rays are just representative. But your eye would say, okay, I see this light ray, I see this light ray, I see this light ray. And your eye would say, oh, wow, this is so interesting. I wonder where all those light rays are coming from. And it would say, okay, well, it looks like this light ray here, it looks like it's coming from somewhere back here. And it looks like this light ray here, it looks like it's coming from somewhere back here. And it looks like this light ray here is coming from somewhere back here. And your brain would say, oh, I get it. The object that I'm seeing from all, well, try again. The object that I'm seeing from all of these reflected light rays is right here. That's where the object is. And so your brain would see 2 things. It would see the actual object, but then it would also see this image of the object back behind the mirror. This image would be upright because you see it right side up. It would also be a enlarged image because you see it much larger. And finally, it would be a virtual image because it's not made up of real light rays, it's made up of light rays that your eye traced back. If you look close up at a spoon, that's exactly what you see. You see your eye, it's upright, it's a right side up version of your eye. It's enlarged, it's bigger, and it's also virtual. It's a virtual image. Now, you can't really see the difference between virtual images and real images, which is why these mirror ray diagrams are really helpful for knowing, is the light actually there or is my brain just tracing it back? Those are the two types of images that you get with a converging mirror. Now, there's also another type of image that's possible, and I should say it's the lack of an image that's possible. If you put an object right at the focal point here, you will get no converging of light rays, and all of the light rays will come back parallel to each other. If all of the light rays are parallel to each other, well then, you're not going to see an actual image. You're going to see no image. And you'll see that there's this weird transition point between holding the spoon far away and looking at yourself upside down. Then there's a point where you can hold it really close to your face and you see your eye right side up. But there's a weird spot in there where you actually can't see anything at all. It's just a blur of colors. Those colors seem to have no direct focus, no point that they're all coming from. They're all just kind of blurred and all over the place. So that's also a possibility that you can see with concave or converging mirrors like this. You've seen converging mirrors in your real life before if you've ever seen one of those nice makeup mirrors. Those nice makeup mirrors are a little bit converging, and the reason why is because they want you to be able to see your face up close. If you get really close to a makeup mirror, you'll see your face way bigger than it is in real life. It's an upright, enlarged, and virtual image. But if you scooch back away from the makeup mirror, you'll see yourself upside down and smaller. It's an inverted, reduced, and real image. Then there's this weird place in the middle where you actually see no image, and that's if you put your face right at the focal point. That's a little bit on concave mirrors. Let's talk about convex mirrors, our last type of mirror for today. Okay, this last type of mirror, type 1 that we looked at today was a plane mirror. Type 2 that we looked at was a convex mirror, or a concave mirror. Type 3 that we're going to look at is what we call a convex mirror or a diverging mirror. Okay. A diverging mirror is what you see when you look at the back of the spoon. Can you go ahead and look at the back of the spoon and make a quick guess as to what kind of image are you going to see when we draw this mirror ray diagram? Let's see if you're right. Here's what we're going to do. We're going to start by drawing our principal axis. As always, please get out your ruler and draw a nice optical axis, nice and straight like so. Then you're going to take out your compass. Once again, you're going to adjust it to the position that you want it at. Draw on your piece of paper a little mark that's going to be your center of curvature and label it C. Then you're going to use your compass, you're going to swivel it around to make a nice convex mirror like this. I like to say in class that a concave mirror is called a concave mirror because it looks like a little cave. A convex mirror is called a convex mirror because it looks like a little vex. It's kind of supposed to be funny and no one ever laughs. Okay, here we go. A diverging mirror or a convex mirror. Once you've labeled C, once again, you do need to label your focal point here, like this. And then let's put an object over here out in the real world. Oh gosh, let's not make a crooked object. A nice little object right here out in the real world, like this. Now here's what you're gonna do for this sort of situation. You're gonna follow, once again, the 3 golden rules. You're gonna take your little ruler here, and I'm not going to use a ruler in case you haven't noticed. I'm not using a ruler. Yes, it is a problem, I understand. Here's what you're gonna do, is you're going to follow the first rule. The first rule says that a line that goes through, a ray that goes through C will reflect back on itself. Okay, well here's the issue. If I draw a nice line, you see that that line is never gonna make it to C, no matter what I do, because there's this mirror in the way, so the light ray can't actually make it to C. So what's going to happen is I'm going to take my little ruler and I'm gonna line it up so that I get a nice line that goes from, well, ideally you would do this with a ruler, a nice line that goes from the top here and would go all the way through C. But I'm not going to draw this whole back half of the line here because the light doesn't actually go back there. So here's what I'm just going to draw. I'm going to get my ruler nice and lined up, and then I'm just going to draw the part from, and that is not good. I'm just going to draw the part from the top here to the mirror, not including the rest of the light ray that would make its way through C. That light ray is then going to reflect back on itself, so I can draw its own reflection. Its own reflection, oh no, its own reflection is going to go, and you could do this way better than me with your little ruler. I'm so jealous. It's going to go back this way, okay? There's your first rule. Let's take a look at your second rule. Our second rule says that a line that goes through F will reflect back parallel to the optical axis. Well, once again, if you look here at F, if I try to make a little light ray that goes through F, well, it's not going to make it there because there's a big old mirror in the way. So what's going to happen is I set up my ruler so that I draw a line so that if that line did keep going, it would go through F, but it's not actually going to go through F. So I draw it nice like this so that it would go through F. Oh gosh, I just am embarrassed by my own lines. It's so embarrassing to not have a ruler. Okay, so this line would go through F hypothetically, but it's not going to make it there all the way. Instead, it's going to reflect back. And when it reflects back, it's going to reflect back parallel to the optical axis like so. Then, my third golden rule of optics is that a light ray that is parallel to the optical axis will reflect back through F. Now, here's the issue here is that okay, stop doing that. Yes, and go away. Yes. Okay. Here's the problem here is I'm going to start parallel to the optical axis, but it can't reflect back through F because F is all the way over here. So I draw a line tracing back where this thing would go if it could go through F. And I say, it looks like it would go back like this. Except you wouldn't just be saying it looks like it would go this way because you would have a ruler. So you would line things up so that this light ray would actually go back through F if it actually did go backwards. Now here's what your eye will see. Your eye will look at the world and your eye will say, oh, so interesting. Okay, let me see what I can see here. Your eye would say, okay, I can see 3 light rays that are being reflected. 1, 2, 3. It would say, let me figure out where these things came from. It would trace this one back here. And it would say, well, it looks like this one that's coming in parallel to the optical axis, it looks like it came from somewhere back here. It would trace back this one that would go through C here, and I would say it would look like it would go something like this. It would trace back this one that would go through F here. Oh, no. And again, this is where you really need a ruler. And it would say it would go something back like this. Really, ideally, this should actually go, okay, try again. Okay, this should actually go through F here. Now, here's where my drawing is bad, and this is where I have said again and again and again, you do actually need a ruler here. Because if you don't have a ruler, these light rays here are not going to converge where they're supposed to, and you need them to converge. But here's what you would see is you would see that there is some convergence point back here where all of these light rays come from. And your brain would say, oh, hey, so cool. I think I get it. I think that the top of the object is back here, back behind the mirror. And so you would have this object in real life, but you would see this image. And you could use 3 adjectives to describe this image. You would say this image is, first of all, upright. It's not reduced in size, it's right side up. Then you would say this image, or sorry, did I say not reduced in size? I mean, it's not inverted. It is reduced in size. That's our second adjective. It's reduced in size, it's upright. And finally, you would say that this is a virtual image because it's made up of fake light rays or light rays that your brain just traced back. Hey, when you look at this thing, we call this a diverging mirror because as you can see here, all of these light rays, 1, 2, 3, do you see that all of the reflected light rays came back pointing in all opposite directions, all scattered out. They're all pointing this way and this way and this way. A diverging mirror diverges light. The only way you can get it to converge and imagine the top of an object is if your brain actually traces back those light rays and sees a virtual image. So all diverging mirrors, all convex mirrors, will always make an image that's upright, reduced, and virtual. And you can see that if you take the back of your spoon, hold it far away from your face, you see an image of you that's upright, reduced, and virtual. Bring it nice and close to your face, you'll see an image of you that's upright, reduced, and virtual. At any distance, doesn't matter, you're always going to see an image that's upright, reduced, and virtual every single time. You see diverging mirrors all the time in bus, on the school bus. If you've seen up at the top there, the bus driver will often have a nice diverging mirror up in the corner. That diverging mirror lets the bus driver see all the way to the back of the bus because he can see an upright, reduced, and virtual image. On the sides of your cars, you have little side mirrors that say objects in the mirror are closer than they appear. Well, that's because those mirrors that live on the side of your car, those are diverging mirrors. They let you see more of the world because they make a smaller image, but as a result, the image is much smaller and so it looks further away. So your car warns you that objects in your little diverging mirror are much closer than they actually appear. But it lets you see around your car better. You've also seen these kinds of diverging mirrors that'll live around corners on bike trails or through tunnels so that you can see to the other side of the tunnel or see around the corner so that you know if an oncoming biker is on their way. That is a nice safety precaution. It lets you see more things. So diverging mirrors always create images that are upright, reduced, and virtual, and they can help us see further or see more of our environment. Take your little spoon and you can see that you can use that little spoon to see all the way around the room if you hold it out far enough. Pretty cool stuff, yeah? Today we talked about 3 types of mirrors. We talked about plane mirrors, concave or converging mirrors, and convex or diverging mirrors. At this point, you should know how to draw 4 types of ray diagrams, 1 for plane mirrors, 2 for converging mirrors, and 1 for a diverging mirror. And that is all for today, folks. I hope you have a wonderful, wonderful rest of your day and that you enjoy all of the reflections in the world around you. Bye, good people.